uh, power refrigeration and heat pump cycles. Is that right? So yeah, like in school, you just have this thing where you're like, I'll bet this is true. I'm, you know, 60% sure this is true. I'm going to go with it and see what happens. But that's kind of like, that's not a good habit to get into generally as an engineer. I mean, everyone gets into that habit in school. But, well, the one time that I, the one job that I had uh, between my two times in graduate school, um, I was I was like the engineer in charge of a biomechanics lab at a children's hospital. And the stuff that I sent to doctors and whatever uh, was, they were going to use that for surgery on little kids or whatever. And there was no one checking my work and telling me I got a 78, or you know what I mean? And so at first it was terrifying. Uh, but I think it really ended up being like you know, uh, a good exercise for me. I mean, uh, to just be like, I'm the last line of defense against these answers. How am I going to be sure? How am I going to figure out without any doubt that this answer I'm getting is right? I mean, it's just kind of a different mindset than the mindset in classes. Um, but okay, so a heat pump cycle. You're trying to keep the inside this temperature. Um, okay, it's over 14 days. Um, I believe that what I did on this one was I ended up doing everything using like um, I think I ended up doing everything in terms of like finite amounts of energy. And so that didn't really end up being a problem. In 14 days, I figured out how many hours there are, and then just multiplied everything by that. And then instead of talking about rates of energy, I just talked about amounts of energy over that 14-day period. I think we did this in class, actually. I think like if you go back to the notes, you can find this problem. Okay. Any other homework questions? Yes. Okay, so we got a power cycle. I am in the habit of always just drawing out what's going on with whatever kind of cycle it's talking about. So I'm going to I don't know, it's a way to get myself centered on the stuff that we know. So here's the system in the middle, uh, the hot reservoir above. Um, so this has a temperature of 1500 Kelvin. Um, and uh, 750 times 10 to the third joules is transferred into the system. And the cold reservoir, which isn't very cold, but colder than 1500, is 500 K. And um, it's discharging 100 times 10 to the third joules. Oh, and there is another heat transfer Okay, so we're going to have two of these. And so this one has a temperature, so another heat transfer from the system, and this is 1,000 Kelvin, and we're not given what this transfer is going to be. Is that correct? So I'm just going to call this QC2, you know? And then this is a power cycle, so we know some work is coming out. And so conservation of energy says add up all the energy going in. That has to be equal to all the energy going out. So going in to the system, we have 750 times 10 to the third. And going out, we have work plus QC2 plus 100 times 10 to the third. And so I'll write that as 650 times 10 to the third is equal to W plus QC2. And we are going to, so we're using the Clausius inequality that says for a cycle, squiggly dq over t around the boundary is equal to negative sigma. And we are given these various values of sigma. So for part A, we have that this integral delta Q over T at the boundary is equal to negative. This is in kilojoules per Kelvin, so 0.1 times 1,000 is 100. Oh, I'll just write it like it is. Bless you. And now let's write out what we know about this integral. So we have positive heat coming in of 750 times 10 to the third divided by 1,500. And then going out, we have QC2 over 1,000. And we also have 100 times 10 to the third divided by 500. And all of that is equal to negative 0.1 times 10 to the third. We only have one variable here, so we can calculate this. I didn't bring my bag. I don't have my calculator. My beautiful calculator. Well, let's go. I think it goes to 400 actually. Okay, so QC2 is equal to 400 times 10 to the third. And this is joules. Oh, yeah, thanks.
I know that's what you use.
Yeah. Sure. I have like one of each one so I could figure out how to do them, but that is the one that I tend to use. Exactly. Where's your lid?
I don't know.
Oh, no.
Most of the last time I dropped it, one of the many.
Oh, no, we should 3D print one.
Right.
Okay, and what else do we have? Well, it's just a bunch of different values. We'll do part C, how about? But let's think about what's going to happen here. So if this is a reversible cycle, then sigma is going to be 0, right? So it would make sense that the efficiency of this thing is going down as sigma gets more negative. Okay. So if sigma is more negative, 0.35 compared to 0.1, would you expect more of the energy that's brought in from the heat from the hot reservoir to be lost in the exhaust, or less of it? If it's so what we're saying is it's getting more inefficient, and so if it's more inefficient, I think what we would expect is that we'd be losing more of, we're paying our hard-earned dollars to make this hot reservoir hot. We want as little as possible leaving in the exhaust. We'd expect for a 0.35 sigma, we would expect this value to be bigger. Okay, so now it's going to be the same calculation. We're doing part C. So this time our integral delta Q over T around the boundary is equal to negative 0.35 times 10 to the third. Everything goes the same, 750 times 10 to the third over 1500. Minus QC2 over 1,000 minus 100 times 10 to the third over 500 is equal to negative 0.35 times 10 to the third. And so we have, I'm going to get everything to 3,000 denominator. So 1,500 times 10 to the third. Minus 600 times 10 to the third. This is over 3,000. Is equal to plus 1.05 times 10 to the 6 over 3,000 is equal to 3QC2 over 3,000. And so 1,500. And so I got that this time QC2 is equal to 650 times 10 to the third joules. Yep.
Professor, for like when we took the squiggly with the circle,
Yeah.
and like so we got the efficiency at like 0.1 kilojoules. So because the unit is joules over Kelvin.
Right. That's what I was using. Yep. Okay. What about the efficiencies of these? Could we figure those out? And which one do you think is going to have a bigger or smaller efficiency?
The one with the
Yeah.
circle with, I don't know group figures that well.
And I guess this is so what are more efficient? What is more efficient, A or C? So let's go back and think about that calculation. So remember that the coefficient of performance for a refrigeration system, this is a power cycle. So the efficiency is this eta, and we're trying to produce work, and the cost is the heat. And if we look back at this thing, we can see that the work is equal to 650 times 10 to the third minus QC2. So 650 times 10 to the third minus QC2 for part A is 400 times 10 to the third, all divided by QH, which is 750. And so you have 250 over 750, so that's 0.3 repeating. Okay, so that's the efficiency for part A. And part C, no. The efficiency is equal to, so again, we have 650 times 10 to the third minus 650 times 10 to the third over 750 times 10 to the third. And that says that the efficiency is 0, which doesn't sound very good. So the
Greatest efficiency is just A, like 33%.
So yeah, 33%. And I have to think about the meaning of that second one.
The middling efficiency, right?
Which one? 0.33?
I thought you were talking about the Giza efficiency.
Yeah, right. Yeah, oh, yeah, right. So anyways, you can see that the efficiency goes down like you would expect compared to those sigma values. Work. The better the closer to 1, the better the efficiency. The work. Well, yeah. So what's happening here is this is as bad of a heat engine as you can get in part C, it turns out, for these temperatures. I mean, you can basically think of giving someone a heat engine that's like a rock or something. It's not doing anything because because you're just, from this calculation, your work is 0. It's not doing anything. You're pumping heat into it and it's all just leaving in the exhaust. Okay. Any questions about that one? So you can't get worse than that. And that's because the work is equal to 0, which is the whole point of a heat engine. All right. So we're starting to talk about the TDS equations. And you all learned what a cursive lowercase s looks like. So that was progress last time. And the TDS equations say there's two of them. TDS is equal to du plus pdv. And the second one says TDS is equal to dH minus VdP. Both of these are always true. There aren't too many things we can say that about in thermodynamics, but this doesn't have any restrictions on it. But we're never going to be able to use these in the full form. From here, we're going to have to simplify in order to make this useful. So we'll never use these in full form. We're always going to simplify them based on our conditions. And the first simplification that we did last time was for an incompressible material. And we saw that delta S is equal to C times the natural log of the final temperature divided by the initial temperature. And remember that these temperatures are in Kelvin. They have to be in an absolute scale. Okay, so let's see this work. So let's say we want to calculate the change in specific entropy for liquid water. As it goes from 30 degrees Celsius to 80 degrees Celsius. And let's just say at 10 bar of pressure. And then we're going to compare that to the website to see how accurate our, we're making this assumption of incompressible. Nothing's completely incompressible, so this is going to have a little bit of error, but for liquids, this is a very accurate calculation. So, okay, in that temperature range, you can look it up in our tables. That C is about equal to 4.18 times 10 to the third joules per kilogram Kelvin. And so the change in specific entropy is equal to, this is 4180. So C times the natural log of 80 degrees Celsius is 273 plus 80, so that's 353 Kelvin. 30 degrees Celsius is 303 Kelvin. And so you get 638 joules per kilogram Kelvin for that change in specific entropy. So now let's go to the website and compare. So at 30 degrees Celsius and 10 bar, the specific entropy so this is for liquid water. And we have a temperature in Fahrenheit of 30 and a pressure in kilopascals of 1,000, I think, right? So specific entropy 436.5 joules per kilogram Kelvin. And at 80 degrees Celsius and 10 bar, our specific entropy is 1075 joules per kilogram Kelvin. And so together, the change in specific entropy is 638.5. So, you can see that's and actually that could have just been that it changed sig figs, so joules per kilogram Kelvin. And so that's a great approximation. Um, so this incompressible assumption gives great results for liquids. Well, if we're going to check against, like if our gold standard that we're going to check against is going to be that website anyways, why would we ever want to do that calculation? Well, that website only has like 10 substances in it. So what if we have some liquid compound we don't have values calculated for us? We could get really good results using this approximation. Any questions about that?
What? C?
C is the specific heat. So that, and to look that up, you can find that for different temperatures in the tables and in complete property tables, and it's pretty early on in the complete property tables. Properties of common liquids, solids, and foods. So this table A3 in here. So you can go down here and this last column gives you the specific heat. So you can see for water around 0 degrees Celsius, it's about 4.22. For 25, 50, 100. So you can just look up the one that's closest to your temperature range to get that specific heat. Any other questions?
So what is American speaking when it's in 100 degrees Celsius, like when it's steam or vapor?
Well, you don't know. Remember that it's sort of natural for us to think about standard atmospheric conditions. But remember that you can have liquid water at a whole huge range of temperatures if you keep adjusting the pressure. So you could have liquid water at 200 degrees Celsius. You just have to have a really high pressure to go along with it.
The way I imagine it goes, like the higher the temperature gets, the more it wants to expand.
Yeah.
The more pressure, the more.
Exactly. That's how I imagine it too. Or like boiling is particles trying to escape, and the pressure keeps fighting them back into the liquid.
Professor, could you scroll down a little bit?
Yes. So the next thing we're going to calculate, we're going to do a similar thing, but for ideal gases. The ideal gas approximations, usually the approximations that we get, they can be just as good, but they're usually not, because we tend to think of specific heats as constant, and that brings error into it. And they're always a little more complicated because there's a little more going on. It's just not quite as simple a case as incompressible. But now we're going to simplify this. For an ideal gas. And, what we're doing again is starting from the TDS equations. So what's the starting point with ideal gases? Let's write down the stuff that we know. Okay, we know that PV is equal to RT, and that R is for a particular gas. That's not a universal gas constant. And the specific internal energy is only a function of temperature. That's true of incompressible and ideal gas. You could also think that this means that H is only a function of temperature. And then using these in the definition of the specific heats for ideal gases, CV is just equal to dUd temperature. And you can use that to write that du is equal to CV dt, which then you could integrate. We do that all the time with incompressible materials. We don't do it quite as often for gases. So why don't we as often integrate this equation du equals CV dt as we do for incompressible materials? It's the same equation, but there's one difference. You saw when we just looked at the C values for water that it varies very little as the temperature changes a lot. Okay, with gases, CV changes quite a bit as temperature changes. So if you really want this to be accurate, you either need to have a small temperature change, or you need to represent that CV as a function of temperature too, which you can do, but we haven't done. Okay, but I mean, it's the same relationship kind of that we had for incompressible. And then the last thing is CP is equal to CV plus R. So those are the things we always know about an ideal gas. And from these, each of the two TDS equations gives a useful simplification, just depending on what you know, what you want. Okay, so first let's start with TDS is equal to du plus PDV. So now we can make the change that du is equal to CV dt. And I'll keep this the same. You with me on that? That's a V. And now we're going to use the ideal gas law. Rearrange that. P is equal to RT over a specific volume. So now we have T ds is equal to CV dt plus RT over V dV. And now divide both sides by T, and we get ds is equal to CV times dt over T plus T divided by T. The T's here go away, and you just get R dV over V. Does R change with temperature? Think of what R is.
The ideal gas constant.
Yep, for that specific gas. And the way you calculate is it's the universal gas constant divided by the molar mass. So it has nothing to do with the temperature. So that one's constant. There's no problem there. The one that is a little bit of a problem is that CV. So R is constant over, well, I guess, any specific volume range. CV isn't constant over a temperature range. But you can assume it is for small temperature ranges. So assume it is for small delta T. And notice that if that CV is constant, if you're treating that CV as constant, this is something you can just integrate.
And what happens if we have a situation where we do have a large temperature range?
Yeah, well, one thing you can do is, like I've mentioned with calculating a relationship between specific internal energy and temperature, is you can figure out, it's pretty easily available, coefficients to represent this CV as a polynomial function of temperature. Okay, and then you're just integrating polynomial that can be kind of ugly, but it's something you can do, and you certainly can do it numerically, with Wolfram alpha or something. Yeah.
What do you consider a small?
That's really, yes. I mean, and that's totally like the important question, and I don't have an answer for you. But I'm going to do an example where we see a pretty big temperature range, and you still, like percentage wise, we don't have that much air, Yes.
I might have missed that. The last step you just divided by T for all of them.
Yeah, divide everything by T. Yep, exactly.
And then you moved R over, so the last term is a little different.
Yeah, that's right.
Yeah.
Because that R is just a constant, so so that can be outside of the integral. Okay, so let's see what my I guess my example is for the other one. So let's just do the other one quick, and then I might have to wait to do the example for next time. But okay, so the second one, we're just going to start with the other TDS equation. So TDS is equal to dH minus VdP. And dH, okay, so we have this equation that says H is the specific enthalpy. And so what we get this fourth equation from is that, remember, Cp is equal to dH over dH dt for an ideal gas. And so you can rearrange this, and you get that dH is equal to Cp dt. So I'm going to use that here. I'm going to replace the dH with Cp dt. And then I'm going to do a similar thing to what I did last time. The ideal gas law says PV equals RT. And so V is equal to RT over P. And so we get TDS is equal to Cp dt minus RT over P dP. And then divide both sides by T, and you get the ds is equal to Cp times dt over T minus R times dP over P. Well, again, Cp isn't constant. Over changes in temperature. But we can assume it is for small changes in temperature. And then you can integrate. Okay, well, that's it for today. But next time I'll start with an example of using these, and we'll compare it to the website. And in my example, I'm going to go from a temperature of 300 Kelvin to a temperature of 1,000 Kelvin. Okay, that's not really what you would think of as a small temperature range. But our answers are going to be within about less than 10%, closer to 5%.
In an actual like engineering or professional setting, is that like way too high?
It really just depends on your needs. You know, I think there are a lot of cases where 5%, as long as you know what your precision is, you know, getting something within 5% is a very helpful thing. Okay.